Hello, this is section 3.7 for Calc AB, and this is the last section in chapter 3, and it's an important section because it'll help us begin chapter 4, but it's called differentials, and there's a couple ways we'll use differentials, and it's mainly in how we're going to write our derivatives and so forth. So it's kind of an interesting section to end on, but it'll make a lot more sense when we start to do chapter 4. Okay, so using a tangent line approximation, you might also hear me call it a linear approximation. That's what we call it in Calc Survey. So if you restrict yourself to a small enough interval around a particular point on a curve, the equation of the tangent line at that point is a good approximation of the value of the original function. Now that goes back to that whole concept of if you zoom into a function, it's going to start to appear like a linear. We say it goes linear as you zoom in. So, and you can kind of see that over here. If I was to zoom in, it would start to look like a line, and you can see how that tangent line there would at least give me a good approximation of the values around my point. Okay, so find an equation of the tangent line to this function at 2, 8. Use this linear approximation to complete the table. So we find we get the derivative and get the slope at 2, and then use the ordered pair 2, 8. So here's our line, our tangent line. And here's the actual values on the curve. So this is us plugging in 1.5, 1.9, 1.99 into the curve. And then these values are what we're using the tangent line. And so you can see the tangent line and the curve share the point. That's why they're the same. And these stay along the line, but you'll notice this is actually pretty good. They're still pretty close. So compared to on the curve, and this is on the tangent line. But you'll notice as you get farther away from your point that they share, so 2.1, it's not as close, it's not as good. And then 2.5, you really start to get different values. Okay. But at least close enough to that point, using that tangent line approximation is going to be pretty good. And in the business world, in Calc Survey, we talk about you don't have a function. You'll want to have a good way of maybe predicting what's going to happen next. So using the tangent line might be a good way to predict, or at least make sure you make enough items for the future type deal. So we use this linear approximation or tangent line approximation in that business calculus class. Okay, so if using a point C and f of C, the tangent line would be this. And notice it's that derivative is our slope. That's the key. Okay, so definition of differentials. Let y equal f of x represent a function that is differentiable in an open interval containing x. Now remember, this word differentiable means you can find the derivative of it. So the differential of x, denoted by dx, is any non-zero real number. The differential y, denoted dy, is dy equals f prime of x dx. So what on earth are they talking about here? So I drew a curve. Remember, we drew this curve the very first day of school. And we pick a point, we pick another point, some change in x away. And the key thing is, you can already find the change in y by simply subtracting the two y values. That's what's here. This is your actual change in y. Okay. Now, then I drew a tangent line through our point. And we get a new dy that appears here. And you can see as you move this point closer and closer to our original point, that change in y, the actual change compared to the dy, get closer and closer together. So the dy is going to be, and here's where this comes from. So y equals f of x, and if you do the derivative of both sides, we can use that Leibniz notation, dy dx equals f prime of x. Then just simply multiply over the dx, and this is the dy. It's the approximate change in y. But here's another good example of why you want to use points that are close to your original point, so that these two distances are closer together, and that's what this table is showing you. You don't want to get too far away from the point that they share. Okay, so this change in y, you subtract the y values, but the dy is the derivative dx, and you can see how they're very close to each other. So important facts to know. The smaller the change in x becomes, the closer the change in y gets to dy. And I've said that, 5 times now, right? And then, and so notice they're saying, well, then the two become approximately the same, and we can replace that dy with the change in y. And so here, they're just reminding you the change in y is the actual change in the y values. Dy is associated with the tangent line. Change in y is associated with the actual curve. All right. Okay, so here's an applications problem. So let y equal the square root of x. Find dy when x equals 4 and dx is 0.1. Compare this value with the change in y for x equals 4 and the change in x equals 0.1. Okay, so first, I did the easy part first. Let's get the change in y. That's just subtracting the two y values. So I plugged 4 and then 0.1 in. So that's here. So that's the 4.1 minus 4. And that's the change in y. Okay. Now let's compare it. So if we do dy, that's the derivative times the change, our dx, our change in x. So I went over off to the side, did the derivative, plugged in 4, and got 1/4 here. So this is 1/4 times our change in x, 0.1, and you get 0.025. And this was the actual change in y. So, our derivative, our differential I should call it, gave us a very good estimation in the change in y. Okay. All right, so calculating differentials. Each differentiation rule from chapter 2 can be written in differential form. So notice you have, this is our derivative form. So du dx equals u prime. Remember, u is always a function in terms of x. And notice all they've done is they've multiplied over dx. And there it is. That's the differential form. du equals u prime dx. Same thing with over here with v. Now there's a reason you might say this is the same. Why did we just change u and v? Well, we're going to use this here in a second. So now when you do the product, you already know it's first times through the second plus second times through the first. Well, watch. They're going to multiply over dx, which is what we have here. And then if you distribute it, look what they do. U prime dx looks really familiar. Oh, we can replace that with du. So we get v du. And then when you distribute here, v prime dx gets replaced with a dv. So we can write this is the differential form, v du plus u dv. Isn't that cool? And that's going to, if you know anything about integrals, you're starting to, oh, I know that. So that's something we'll use in chapter 4. Okay, and then adding and subtracting, you can write it this way as well. And then scalar, the scalar doesn't really do much. It behaves just like it would in a normal derivative. And then here is your quotient. So, and it can be derived the same way. I wouldn't worry too much about this. This is all going to be used in the future, so it's just making you aware right now. For your purposes, find the differential. For now, we're just going to simply find the derivative like normal. Find the derivative, and then at the very end, you're just going to simply multiply over the dx, and you'll just leave it like this. And we typically write the dx at the end. So I had to use chain rule to do the derivative, and then I just simply at the end, instead of writing dy dx or y prime equals, I'm going to write dy multiply over the dx, and that's how you leave your answer. And now it's in differential form. And the same thing here. And you can write the dx in the numerator, or you can write it off to the side. But just realize it's multiplied and always in the numerator. Dx should never end up in the denominator or inside parentheses or anything like that, or under a radical. Okay, now here's another fun little application. So using differentials to approximate function values. So this is kind of fun. So use differentials to approximate this 1.99 squared. So you would be pulling out your calculator and trying to figure this out, but watch how this works. So if I make the function x squared, and the derivative is 2x, and I'm going to use, because isn't 2 really close to 1.99? Yeah. So let's use what we know. Start with what you know. 2 squared is 4. And then we'll use our derivative at 2 and the change in x. So we end up with f prime of 2. So we're using this formula here. So you're starting with what you know and you're adding the approximation to it. So the derivative at 2, well, plug 2 in, you actually get 4 again. And then our change in x is negative 0.01. So if you put that in the calculator, you get 3.96, which is very close to the actual 1.99 squared. So the whole idea is let me go back up here so you have a visual, is you're starting with this point that you know, and we're staying along that line to get an approximation. So we're definitely going off of the curve, but we're staying along that tangent line to get an approximation. So just like in this table, we stayed along the tangent line and got this number as opposed to the actual number on the curve. So this 3.96 is staying along that tangent line. We're starting with what we know. We're staying along that line. We're using the slope of the tangent line and the change of x to get an approximation. Right, and then we did the same thing here. So we created a function x to the 1/3, did the derivative. Ooh, that's missing a tick mark right there, isn't it? So that's the derivative. Don't know what happened to my little tick mark there. Then plug in 8, start with what you know, plus, and then the derivative at 8 times the change in x. Now this one's not going to be as good of an approximation because we're kind of getting far away. 0.7, that's a pretty big change in x. So this isn't going to be as good of an estimation as we did in example 6. Right. So I always tell Calc survey students, start with what you know and you build from there. And you stay along the tangent line to get at least an approximation. And then here's another applications. So error propagation. So let x be the measured value of a variable and let x plus the change in x represent the exact value. Then the change in x is the error in measurement if the measured value x is used to compute another value, f of x, then the difference between these two is the propagated error. So I kind of labeled what's going on here. This is your exact value, your measurement error. This is your measurement value, and this is your propagated error. So let's read through this little example real quick. So the measurement of an edge of a cube is found to be 12 inches with a possible error of 0.03 inch. Use differentials to approximate the maximum possible propagated error in computing. So the volume of a cube, this is your possible error for each side when you go to take your measurement. So when you take the volume of a cube, I did the derivative, and then here's where I'm going to use this formula. So I've got the dv equals, so I wrote it as a differential, and I'm going to replace that dx with my 0.03, and it could go either direction. So when you multiply, you have your 3x squared. So 3 times 12 squared times your dx. You get plus or minus 12.96. That's your propagated error. Okay, so you might say, Cogswell, where is this coming from? Because that's not the formula up here. But remember, we said earlier that this change in y is approximately the same as dy. So you can use your f prime of x dx, that differential. That's how we're using our differential to get this approximation, which we can say is pretty close. Okay, and then here's just relative error of part A. So if you take the derivative and divide it by the original, so we took the derivative and divided by the volume function, plugged our dx, replaced it with plus or minus 0.03 divided by 12, that's your percent error. And then the surface area of the cube, we found the propagated error doing that. Use that for our formula, and then relative error with that. So it's just interesting to see how 0.03, when you're going to measure something, can have such a drastic effect on the actual volume of the end product. So, okay, so the main thing is find the derivative, move that dx over. That's the key. That's how you write it in differential form. Okay, But definitely do your homework because these can be some interesting problems.